Now we're going to look at 3 new definitions. So the first one is we're going to say a relation R defined on a set A is called reflexive if X is related to X for every X in A. So every element in your set needs to be related to itself. So let's look at an example here. Let's say our set that we're going to look at is S. It's going to be the set ABC. And we're going to consider the following relations defined on S. So the first relation I'm going to look at is going to be called R1. It's going to be the relation A relates to B, B relates to A, and C relates to A. And then we're going to look at the second relation. A relates to A relates to C, B is related to B, C is related to A, and C is related to C. So if we look at this first relation here, and I want to know, is R1 reflexive? Well, it's not reflexive. So the relation R1 is not reflexive. And why is it not reflexive? Well, because there's an element that's not related to itself. So for example, the pair AA is not in R1. A is not related to itself. But if I look at R2, and I look in my relation, I see A is related to itself, B is related to itself, and C is related to itself. So R2 is reflexive. So since AA, BB, and CC are in R2, the relation R2 is reflexive. So now let's look at our second definition. We're going to say a relation R defined on a set A is called symmetric if whenever X is related to Y, then Y is related to X for all X and Y in R, or in A, sorry, for all X and Y in your set A. So if we look back at our examples from before, so if you look back at R1 and R2 from above, right, so I'll just remind you, R1 consists of the set AB, B is related to A, and C is related to A. Well, R1 is not symmetric since C is related to A in R1, but the flip, the reverse of that, AC, is not in R1. But if I look at R2, which was the set AA, AC, BB, CA, and CC. And if I look, I don't need to look at these ones that are repetitive, because if I flip them, AA, BB, and CC, they would be the same relation. But here, if I look at this one, AC, and if I flip the entries, I would get CA. So R2 is symmetric. Because if I take any one of those the ordered pairs there and flip them, I would get a resulting ordered pair that's also in R2. Okay, and our last term that we're going to look at is going to be transitive. So we're going to say that a relation R defined on a set A is called transitive if whenever X is related to Y and Y is related to Z, then X is related to Z for all X, Y, and Z in my set A. So again, let's revisit our earlier example. So just to remind you, R1, look back at R1, it's the set AB, BA, and CA. And so if we look, R1 is not transitive because, well, I have C is related to A, and I also have A is related to B, but C is not related to B. In order to be transitive, if CA is in my relation and AB is in my relation, then CB would have to be in my relation, but it's not. So then if you look at R2 would be, look back at R2, I'm going to write it here so it's easy for us to reference. And if you check all the elements, so here, for example, I could take A is related to A, and then I also have A is related to C, and then if I take the combination now, A, C, my first and then my last there, that needs to be in R2, but it is. So if you notice, you don't need to take any of these elements actually that have repetitive entries in them, because when you combine them, like I did here, you'll see that you end up with the same element of R2 that you had to begin with. So I don't need to focus on those elements, so the only other combination I can take is AC, as in R2, and CA is in R2. So then if I take again this first and this last one together, I would get AA, which I do know is on R2. And then I could take the flip of that, CA is in R2, and AC is in R2. So because these entries are the same here, I take the combination, the first and the last here, CC, and if I look back up, CC is in R2 as well. So R2 is transitive. So again, when you're checking transitive, you don't need to consider, so go back to our definition. Remember it said whenever X is related to Y and Y is related to Z, then X is related to Z for all X, Y, and Z in A. What we learned is that it is not necessary to check the case X equals Y or Y equals Z.